All right. Okay, everyone, take your seats, please. There's lots to do. There's a quiz to do and stuff like that. So it's not going to be difficult. So, okay. So where we left off last time was analyzing the runtime of something like this, right? So the idea was basically, okay, we have a Python function and we want to know how efficient it is. And what we realized is, okay, we can't really tell you how long it's going to run because that depends on the length of the input, that depends on exactly what's in the input, and that also depends on the computer. So we said three things, right? So we said we want to know what is the runtime proportional to, rather than what is it in seconds, because different computers are going to take different amounts of time, but hopefully it's proportional. So one computer takes like whatever, like 2 seconds per operation, and another computer takes 5, but it's hopefully about constant. We're saying for an input of size or sometimes magnitude n, so not for any input, specifically for an input of size n. And in the worst case, meaning that for example, a list of size n, for some lists, it might be faster than for other lists. So we're saying for the worst kind of list that's still of size n, what is going to be the runtime? Right? And then the way we did it, at least initially, was to say, okay, we can't count seconds, but we'll count something like operations. In the handout that's on the website, what they did is instead of counting operations, they said, oh, I'll just count comparisons. And what I mean by I'll just count comparisons is I said, well, like anytime I check is L at mid greater than E or not, that's what counts, not an operation, just a comparison operation. And sometimes it's subtle, right? So sometimes it's going to be the case that what you count matters. But a lot of the time it doesn't, right? Because you can kind of see, okay, like what's the number of operation? Well, it's kind of like the number of lines in the code, right? Because it's like about 2 operations per line or something like that. And then how many comparisons? Well, it's also kind of the same because, you have an average of like half a comparison per line. So whether you count lines or whether you count comparisons, it's all going to be proportional anyway. And given that we're asking what is the runtime proportional to, it doesn't matter where we say how many lines or how many operations or how many comparisons. For the people who did the lab today, what we counted was, and for the people who do it tomorrow, that's already on the website, so you can have a preview. So what we asked was like, how many times did this block of code repeat? How many times does this run? Yes. It definitely is. I'm on the website and it's there, so. Okay. All right. So that's the general thing. Sometimes it's going to be a little bit subtle. So in the sense that sometimes it's going to be the case that some operation is actually going to take time that depends on the size of the input, for example. And we'll get to that later. But for now, basically counting the number of iterations, so counting how many times the thing repeats, or counting the number of operations, it's all going to be proportional. And so I'm not going to make you on the exam like count either operations or anything like that. The question on the exam is always like, what's the runtime complexity, right? And the basic question is, well, what is the runtime going to be proportional to? So the reason I'm not being more explicit about this is because there are subtleties that I don't want to get into right now. But that's the basic idea, is like, how many times does this loop repeat? How many lines are run in total if you count this block of code running several times as like this many lines times the number of iterations? Those are all the same questions because the answers are all proportional. It's like asking like how many hours. Well, it's the same as asking how many minutes because there's just a constant of proportionality that's just 60. Make sense? So, okay, so that's what we're asking. So now I want to answer this question for binary search. So here's how you can answer it. So we're starting with low equals 0 and high equals length of L minus 1. Let me copy and paste. So I'll let you copy and paste as well. So we are starting with low equals 0 and high equals length of L minus 1. And then every time what happens is we either change low or we change high, right? So what we can do is we can say, okay, so during iteration 1, high minus low is length of L minus 1. And then when we're done with iteration 2, high minus low is going to be twice as small. In fact, a little bit smaller because we're doing like mid minus 1, mid plus 1. So the distance between low and high is a little bit smaller than half the previous range, but approximately this much. And then iteration 3 is going to be approximately, in fact, less. And so on until we get to iteration k, when high minus low is approximately 1. So if the question is, how many times does this loop run? Well, the answer is k, as much as it takes to get from length of L minus 1 down to just 1. So here, like we already had a preview last time, so you kind of probably know the answer, but just a refresher on how logarithms work. So log 2 of n is k such that 2 to the k is equal to n. That's just the definition of log 2n, right? And that turns out to be the answer. So the reason this turns out to be the answer is you can look at it like this. So you can say, okay, so here we're starting with approximately n. And here we are at approximately n over 2. And here we are at n over 4. And here we are at 1, which is equal to n divided by 2 to the k. Why is that? Well, because this is n divided by 2 to the 0. And this is n divided by 2 to the 1. And this is divided by n by 2 to the 2. And so on. So here, like 1 corresponds to 0, 2 corresponds to 1, 3 corresponds to 2. So here it's in fact 2 to the k minus 1. So I want to fix this a little bit. So I'll just change this to 0. So that it lines up nicely. Right. And here it's like, okay, so at some point, 1 is equal to n divided by 2 to the k. That's the same as saying 2 to the k is equal to n. So k is equal to log 2n. Make sense? So it's just a question of like, okay, like if you divide by 2 every time and then after k iterations, you are at 1, well, that must mean that n divided by 2 to the k is 1. So that means that n is 2 to the k. Right? So, okay. So what this means is that the number of iterations performed is approximately, so there is like some approximation here because it's not exactly over 2. There's like a plus, it's in fact a little bit less, but it's approximately log 2n, where n is the length of the list in the worst case. So why do I say in the worst case? Because in the non-worst case, you can just say return mid right away when L at mid is equal to E. So that means that there would be fewer iterations than that. And that means that the number of operations, however you define operation exactly, is A times log 2n. And that's because basically you're going to say, okay, like how many operations is this block? Whatever it is, it's A, as long as it's a constant number of operations per block. Well, it's some number of operations. And you have log 2n iterations. So the number of operations is A times log n. which is proportional to log 2n. So that means that the runtime in the worst case is proportional to log 2n. All right, there's a quiz. Please go to Quirkus and do the quiz. There's just one question there. It's not difficult.
There's no question.
Wait, there is no question again? Yeah, that's I'm sure it's the same. Why is there no question though? All right, it's gonna be the same thing again, but let's try it. Sorry, I'm not sure why, because it was there, but is there now? Is there one now or? No, I mean, it's right there. You don't see it? Oh, that's annoying. So you don't see it? No? All right, well, never mind. The point is that there could be a quiz, so you should come to a next lecture as well. So, so okay. So I consider this a job well done. So okay. We'll try to fix it, or like the semester is almost over anyway, so who cares? But okay. So all right. Back to this. So yeah, so sometimes, you know, like it's like with taxes, right? So like it's not like there's gonna be an audit probably, but just because there could be an audit, you should be honest on your taxes. So okay. All right, so we were here. So now what I want to do is something that like not everyone likes, but some people do, and I want to like rigorously define what we mean by complexity. So here's the definition. And this is, for now, this is not to do with complexity. This is just math, like for any function. So f of n is big O of g of n. And this is, so informally what we mean is f grows at most as fast as G. So f of n is proportional to G or grows more slowly. So for example, so we'll give like a rigorous definition in a second. So for example, n is O of 0.5 n because those are proportional. And similarly, n is O of 1000 n because those are also proportional. And for example, square root of n is O of n because square root of n does not grow as fast as n, right? So square root of n is proportional to something that grows more slowly than n. On the other hand, n squared is not O of n because n squared grows faster, right? So one way to get at this is to say, okay, like let's take the limit of the ratio, right? So let's compute the limit of f of n divided by g of n as n goes to infinity. And if f doesn't grow as fast as g, that means that g eventually is going to then g is eventually going to become larger than f, right? So this could be if n is not f is not as fast as g, then it could be 0, or it could be a constant if f and g eventually settle down into just being proportional to each other. So that's not the definition of big O, and it could be. It's just that for some weird situations, it doesn't fit. So specifically, imagine that f is kind of wavy and also g is kind of wavy. So imagine, for example, that those would be weird, but imagine that f of n is like sine of n and g of n is cosine of n. Then what's the limit of f of n divided by g of n? Well, nothing. It never settles into anything. Yes.
What if the limit goes to 0? That goes
So big O specifically refers to going to infinity. You can make definitions that are.
What I meant is if f of n over g of n goes to 0.
Yes, well, so constant includes 0. Yeah. Okay. So, but yes, that's a good point. So what about n squared O of n? Well, if n squared divided by n, well, that goes to infinity because n goes to infinity when n goes to infinity. On the other hand, if you do like square root of n divided by n, the limit of that goes to 0 because n grows much faster than square root of n. So that means that that limit is just 0, and that's like one of the possible constants. So I was saying this definition doesn't quite work. And the reason it doesn't quite work is because of this kind of deal where f of n divided by g of n here, it never settles into anything. Okay. So in order to make this more robust, and that makes life a little bit more difficult right now, I'm not going to test you on kind of those calculus definitions, but technically the correct definition is lim sup of, so this is pronounced lim sup of f of n divided by g of n, as n goes to infinity is constant. So soup, you know this as least upper bound. And you can basically think of it as max. So basically we're saying lem of max, and I'm not going to test you on this, but like maybe you kind of find it interesting, of n1 goes to n, of f of n divided by g of n. And then here n goes to infinity. So the idea is you take the max of, this would be n1. So you take the max of this ratio above n, and then you keep advancing where you're starting to take the max at. So if you're not interested in this, just think about it as the limit. That's completely fine. The reason it's like that is that, so the reason it's like that is because that takes care of this kind of deal. So the ratio of sine of n and cosine of n, that can vary, but it's limited to within a certain band. So if you take the max over all the possible n's that are greater than the threshold, well, that's going to be defined. So the other thing, and that's really getting into the weeds, is it's not max, it's soup, which is least upper bound. The reason for that is, as you might know, for any bounded set of real numbers, there is always a least upper bound. There is not always a maximum. Right? So for example, did you do that in calculus yet? Yeah, okay. So that's, so see, that it's actually useful. So here you might imagine that, like in the most general case, there would not be a maximum. In fact, quite often there wouldn't be a maximum, but there would be a soup. Not going to test you on this. So what you need to understand from all of this is there is a rigorous definition. And also informally, we're looking of, does f grow as fast as g or less? And what does it mean? Well, it means that if you take the ratio of f of g, does it settle into something constant, in which case f and g are just proportional? Or does it go to 0, in which case f doesn't grow as fast as g? All right. So not going to test you on the definition. It's just that, well, if you don't define it, then you don't know what you're talking about. Of course, if the definition is annoying enough, you also don't know what you're talking about. Okay. So what we say, going back to the analysis of binary search, we say that the asymptotic, and worst case runtime complexity of binary search for a list of length L is O of log n. I left out the 2. I'll explain why in a second. So asymptotic refers to the idea that this is for large n. And this definition is like, eventually it's going to settle into a constant, right? So in the beginning, there could be weirdness. Worst case means that for a list of length n, we're looking for the list that produces the longest runtime. And here we're saying it's going to be proportional to log n, right? So going back to this definition, it would be that there is an actual runtime. There is some kind of function that's like binary search runtime. Of n, and what we're saying is that this function binary search runtime is of log n, right? So the ratio of the runtime and the function log n is constant. So technically, according to the definition above, it's true that it's also O of n to the 1000. And that's because as long as the runtime doesn't grow as fast as whatever is inside the O, that's technically correct. For that reason, on exams, I take care to say the tight upper bound on the asymptotic worst case runtime complexity. And tight upper bound means, well, you don't get to say, oh, it's O of n to n to the bajillion, that ought to be enough, and have it count as correct. So tight upper bound means like, give me something reasonable. Okay. So I left out the two here, and the reason is actually the logarithms are all proportional to each other. So you can just prove if you're interested that log whatever, so log base b of n is equal to log of n divided by log b, where here log could be like whatever you want, doesn't matter because they're all proportional. So it could be the natural logarithm, or it could be the base 10 logarithm. Interpret that as you like. They're all proportional anyway with this kind of constant proportionality. So to be more explicit about it, for example, you could say that log 2 base n is equal to log n divided by log 2, which is itself equal to log 3n divided by log 3, all of that divided by log 3, 2 divided by log, so log 3 divided by, log 3, 2, log 3, 3, and then the log 3 just cancels out. Okay, so the lesson here is that log v1 of n is proportional to log v2 of n with some constant proportionality, which you can work out here. So we just write O of log n because that's proportional to log 2n, that's proportional to log 3n. And we don't care about constants or proportionality anyways, because n is O of 0.5n, and it's equally also O of 1000. Make sense? Questions? Yeah. Yeah.
Oh, wait. So TFX is like more than the complexity model of like the number of the runtime.
All right. So I'll kind of like say it in my terminology. So we're asking this function, for example, binary search, how long does it take? The kind of answer that we want to provide is, well, it's going to be proportional to log n. Okay, so the way we're kind of needing to define it, if we want to be precise in math, is we're going to say, well, like there is this function, a mathematical function, that's like you give me the length of the list and I'll give you the runtime, right? So maybe we'll just name this function binary search runtime. And I'll say, well, like this binary search runtime is O of log n, for example. So that means that binary search runtime for a list of length n is going to be proportional to log n, right? So so this is the G that you're asking about. So in this definition, we just gave a general mathematical definition. It doesn't have to do with runtimes about what big O means, right? And then we're just applying that. Does that make sense? Yeah, okay. So that's that. The upshot is that binary search is O of log n. And that's a big deal. So I put the question in the lab for today and tomorrow. So some of you haven't seen it. Some of you have. So for you, this shouldn't be a surprise how much of a big deal it is. But it is a huge deal, right? So linear search is O of n. The runtime is proportional to the length of the list. Binary search is O of log n. So the runtime is proportional to the logarithm of n. And the logarithm of n grows really, really slowly, right? So you take a number like this much. And what's the logarithm of this? Well, the base 10 logarithm would be 1000. The base 2 logarithm would be I'll just compute it, but I'll give you a way to do it fast by yourself as well. So this is this, and this is not a surprise because all logarithms are proportional. So the base 2 logarithm is always going to be about times this much times 3 point something of base 10. All right. So that's not a lot at all, right? So the linear runtime would be proportional to this, whereas the binary search runtime would be proportional to this. So that's a big difference. Make sense? So that's a big deal. So a brief digression, and actually people ask about this in interviews, maybe still, they certainly used to, where you're asked to like quickly estimate the base 2 logarithm or something, or the base 10 logarithm or of something. So the basic idea is like this. It happens that 2 to the power of 10 is 1032, which happens to be approximately, obviously, 10 to the power of 3. Right? So from that, you can get anything, because that means that 2 to the power of 10, for example, squared is 2 to the power of 20, is approximately 10 to the 3 squared, which is 10 to the 6. For that reason, in fact, people would, if you are talking about computer storage, right? So sometimes 1032 and sometimes 1000 bytes is a kilobyte. And similarly, 10 to the 6, so a million bytes is a megabyte. Or approximately, or 2 to the 20, which is approximately this much. Right? So that kind of thing where you can just say, well, like if you square this, it's 2 to the 20. Sorry, this is squared, of course. If you square this, it's 10 to the 6, and those are still the same, can be used to compute any kind of logarithms. Make sense? Yeah. Yeah, pretty sure. Yeah.
Great. 2 to the 10 is 2 to the 40.
2 to the 10, what? No, not minus. It's like approximately. This is the way we think. Yeah. Yeah. Okay. So some people kind of instead of saying like so like they have like various different conventions for like distinguishing like one kind of megabyte from another kind of megabyte. Like one is a million, one is like 2 to the 20. But not gonna get into it because it's confusing and nobody really uses it that consistently. So, okay, that's that. So I now want to talk about other kind of complexity. So far we saw linear search, which is like dot index. And that was O of n. And then we saw binary search. And that was O of log n. So what other kinds of complexities might you observe? Well, here's an example. Let's say that you say something like for I in range n, and then you say for j in range n, and then like you do something. So you start with s equals 0, and then you add 1.9 every time. So what's the runtime complexity of this? Well, so again, usually what you want to do is you want to count the number of iterations and then just claim that it's proportional to the number of operations, and then say that's proportional to the runtime. So how many iterations is that? Well, so this is n, right? Because you're saying, sorry, quiet down, please. Give me 8 more minutes. Quiet down, please. Thank you. You know, like if I didn't have to say this, we could have so many more quizzes. It would be great. So, okay. In the safe time. So, okay. So this is n iterations, right? Because this repeats n times. And then we're saying repeat the repeating n times, right? So we're kind of saying repeat n times, repeat n times. So how many is that in total? Well, it's n times n, because you're repeating n and then n and then n, so n times, so that's n times n in total. So that is O of n squared. And in high school, I think a lot of the time, or sometimes maybe in my course as well, I try to avoid it. People just say, oh, like if it's a nested loop, that's O of n squared. Well, usually, yes, not always. You got to think about it. So right away, I want to give an example where it's a nested loop, but it's not O of n squared. So you might say something like for I in range n, and then the easiest thing for j in range n squared. What is this? Well, it's the same pattern, right? So here I'm saying repeat this thing n squared times. And then you're saying whatever you're repeating n squared times, repeat n times. So how many times in total? Anyone? N cubed. Yes, thank you. Right, so this is n cubed iterations. So this is O of n cubed. A trickier thing that could happen would be it looks like you're doing n cubed iterations, but the runtime is not actually proportional to n cubed. So that could be actually as easy as something like this. So let's say that here I'm saying multiply by 10. And let me make this be something like reasonable, like 5,000. So you try to run this. And we're not having a good time. It's not finishing running. Right? So there is a tiny change that you can make in order to make it run in a reasonable amount of time. So if I say something like plus equals, okay, I think I broke it. Okay, not happy about this. So if I say plus equals, in fact, that's still integers. Okay. So 5,000 cubed is not like a tiny amount, but that is going to finish running pretty soon. On the other hand, if you say something like times equals 10, what you're doing is you're trying to compute the number 10 to the 5,000 cubed. Because you're saying multiply by 10, 5,000 cubed times. That's, first of all, a huge number. Second of all, because it's an integer can in principle actually store this huge number. Maybe not this much, but it can try to get to that number. So that would take a really long time. Because even to kind of write down this number 10 to the 5,000 cubed, well, that would be 5,000 cubed digits. That's a lot of digits. So the key here, that's also kind of slow. So the key here is that if this is integer multiplication, this would take longer when S is large. Because you would have to basically compute a larger result. Because integers, as you remember, are unlimited. This thing is not actually one operation. You can't just assume that it takes the same amount of time every time. In fact, it takes more and more as grows. For that reason, it just would not finish running. It would be very slow. So this is not O of n cubed. What it is exactly would have to be deferred to ESC180. The thing to remember is when you're just counting iterations, you've got to pay attention and say, does every iteration actually take the same amount of time? In this case, no. All right. Yes. Sorry, I can't hear you. I'll tell you in ESC190. It's not an easy computation. Yeah. Okay. All right. I'll see you. Bye. Thanks.